Good afternoon, ladies and gentlemen. Also on behalf of Jens Fennen, I welcome you here. Jens Fennen, of course, being the one who did all the hard work for this presentation. I was just the lucky one in the draw to come and present it here. Talking about enzymes, what do they do? What are they and how do we use them in the leather industry? Enzymes are biocatalysts. They're catalysts like any other catalyst. They speed up a reaction. They increase the rate of the reaction, but they do not change the equilibrium, and they do not get consumed in the process of the reaction. They're very effective. They speed up a reaction millions of times from a corresponding uncatalyzed reaction. And very important for enzymes, it's a very specific reaction. We talk about the lock and key system that the enzymes work. Like all catalysts, we have a substrate in a certain energy level, and to make it react, we bring it to a lower level of energy. By doing so, we have to overcome reaction energy. That's like climbing over a mountain, and using a catalyst is drilling a hole, drilling a tunnel through the mountain to get from A to B. A very simple explanation of a reaction for this, I've got to prepare a little something. We just, in the previous paper, spoke about hydrogen peroxide. I could have made, presented just a clip, but much more interesting to do it here, in this way. Please, those in the first row, I do not take any responsibility. Allow me. I got here about 18 milliliters of hydrogen peroxide. To visualize the reaction that takes place, I put a little bit of fairy liquid.
I was going to say, is that an advertisement?
I certainly won't get anything out of it. As you all know, the hydrogen peroxide left open like this here, over a period of time of maybe 2 or 3 months, the oxygen will be liberated, and what is left behind is just water, because it goes from one energy level to a lower one by liberating the oxygen and leaving the water behind. By using a catalyst, in this particular case it's an iodine ion in the form of potassium iodide, I speed up the reaction quite substantially. This is a 1 liter measuring flask. Hopefully all of you can see this. We'll let it do its job. I'll come back to this one here later. That's got another purpose to serve. What happens during this reaction, it's a highly exothermal reaction. So by developing a certain amount of heat, this again speeds up the reaction, and we'll see it happen as we go along. Well, let it do its own thing. Back to enzymes. There's a number of classifications in enzymes, and the ones we use in leather making are all of them hydrolases. Some peptidases and esterases. Some of the history on enzymes. They have been used for thousands of years, in particular making alcohol and cheese. In the 17th and 18th century, it was understood that digestion from stomach secretions would convert starch to sugar. 1877, Wilhelm Kühne was the first one who brought in the word enzyme, what used to be commonly known before that as ferments. But until the end of the... Supposed to? It's liberating the oxygen out of the hydrogen peroxide. Come on, don't leave me stuck there. It's coming on. We continue with this. Until the end of the 19th century, it was believed that enzymes could only work in living organisms. But in 1897, it was Edward Buchner who showed enzyme activity in a non-living cell. And only in 1926 was it shown that enzymes are proteins. Ah, thank you very much. What are enzymes? Well, they're globule proteins, macromolecules built from amino acids. They're water-soluble and they're globe-like shaped. Those of us who have been in these famous halls have had some amino acid theories, and we had all to learn about protein structures. There's the primary, secondary, and tertiary structures of proteins. We know there exist 20 different amino acids, and it's their sequence which makes them the particular product of a protein there is. Commonly, enzymes have 100 to 300 amino acid monomers. Spill anyway? There is a three-dimensional structure of a protein here. We've got sheet structures, and it's the combination of those that make up an enzyme, a very complex structure of different types of sheet and helix structures. The yellow thing you see there is the active part. That's the one that works as a catalyst. And here we come to the key and lock principle. The grey thing being the enzyme, the catalyst, and the substrate colored in green will be latched onto. A reaction will take place similar to this catalytic reaction, and will produce products. The enzymes itself at the end of it being available again for the next reaction. We have a number of conditions that interfere or affect an enzyme reaction. One of them being temperature. From the baking process, we all know it's between 30 and 35 degrees. That is a very favorable temperature for enzymes to do the job of baking. If we go too high with the temperature, we reach a point of denaturing the enzyme and destroying it completely and irreversibly. Likewise, pH is a very important aspect in enzyme activity. The first one you see on the top left is the one commonly seen with activity of a baking enzyme. Then we have the one next to it, which have a very high resistance to alkalinity. Those are specialized ones found for soaking and liming, but also lipases are that type of enzymes. Like on the acidic side, and those papains that have a regular and constant activity over a very wide range of pH. The rate of reaction and the concentration is a linear one, as you see in the first picture, but it reaches point of saturation at which it will work optimally, but it will not increase further in its reaction condition. We have activating and inhibiting effects on enzymes. Certain enzymes need, for example, a vitamin to fully function and being optimally used. By contrast to inhibitors, of which we find reversible and irreversible ones, like the too high temperatures are definitely irreversible one. And we have competitive and non-competitive inhibition, meaning to say that a competitive inhibitor is a substance in that environment which reacts like the material that you want reaction to take place, and the enzyme will work on one and the other, therefore reducing the reactivity of the process that we want it to do. And the non-competitive inhibitor is an agent that will, for example, change the structure of the enzyme to such an extent that it will slow down the reactivity of the enzyme, or the activity of the enzyme. We can safely say that over the shelf life of an enzyme that's kept in a store in a dry and cool condition maintains its full reactivity over that shelf life period of time. But as we use the enzyme in process, it's, though not reacting with, not being partaking in the reaction and being consumed by the reaction, it consumes itself. And as a general figure, we would say within 4 hours, the enzyme will reduce, the enzyme reactivity will be reduced by half. So self-consuming, and therefore in the end no longer be a component in the process, besides the fact that the enzyme is a large molecule and it's soluble in water and can be readily washed away. Measuring enzyme activity. Now, very, very often I'm being asked, well, what's the LVU of your enzyme? To which I respond, I don't know. Well, I might know, but I won't tell. The reason being this, and that's very important for me to bring across. I think that's done its job. It's still warm there. The LVU analysis is with a standard substrate casein. It's at 37 degrees and it's at pH 8,2. And it tells us how much casein is broken down over a period of time. Or in other words, how much cheese is being digested. Because casein is principally cheese. In ring tests, by sending a particular product around to different laboratories, it is found that there is lack of consistency from lab to lab. This is just in the concept of the enzymes, and that's the analysis of such. So there is a measure of discrepancies along that line. LVUs is not an absolute figure. But why we do not actually, we do use LVUs purely as quality control measures, but why we're not using it as an information to the customer is the following. Let's, for example, take a very concentrated enzyme of 10,000 LVUs. That is 10,000 LVUs at 37 degrees and pH 8,2. Now, your process of, let's say, baking may be at 29 degrees and pH 9.5. And although it was measured as a product of 10,000 LVUs, in other conditions, it might do virtually nothing or very, very little. More dangerous, however, is the other way around. If you have a product of, say, only 500 LVU, again under these conditions digesting cheese, it could be that away from these conditions, it could be even a dangerous product of very high reactivity and reacting with agents you don't really want to take part in leather making. And we regard it as our responsibility and task of providing enzymes to the leather industry, that we test our products, control that even if you're overdosing the product, there is no harm happening to the leather and to the hide structure. And we propose a given concentration where it does its optimum job. So comparing one LVU with another one from one supply house to another is, in our view, not of relevance. That's why I took a point to talk about LVUs here. The manufacturing of enzymes, it can be from living microorganisms, as we find in alcohol making, yeast fermentation of bread, and use of lactobacillus for conservation. the making of insulin and baiting enzymes might use pancreatic tissue to make them. And more so in later days is the microbiological production of enzymes, growing microorganisms, and by genetically engineering a microorganism that will produce a specific enzyme. So you steer the production of enzyme by controlling what bacteria or what microorganisms you grow. A little bit of history. Now, we've been talking about the smelly business of leather making. Of course, the dog manure was one of those things that were not very pleasant to be used in leather making. All of these, however, are enzymatic processes. It was only in 1907 that Otto Röhm introduced an enzyme for baiting that now was steering away from the smelly business of baiting in the past. We at TFL, of course, regard ourselves much of heirs of Otto Röhm, TFL being made up from Ciba-Geigy, Stockhausen and the Röhm companies. And Otto Röhm, he was really a very inventive guy. Besides making the first industrially available enzyme for the leather industry, plexiglass. That's why I brought this. This is the real reason why I brought this here. Plexiglass was invented in the late 19th century. Not by Otto Röhm, however, but he worked at the beginning of the 20th century quite extensively with this material, and he found it very perplexing to work with it, with the versatility of the product. And it was only in 1933, it was actually Otto Röhm that registered plexiglass. The story says that having been perplexed by the versatility of the material, that plexiglass has got this name. And it revolutionized the car and aeroplane industry by, besides others. Just look at this photograph here of a 1937 racing car, which sheet glass could never allow to make this kind of design. So there we are, that's the model. Back to baiting. Now all of you know the desired effects of baiting, and I don't need to go into details of this. We have the availability of pancreatic enzymes, as I said, but we also have bacterial and fungal proteases that are used in baiting for reasons of working in slightly different pHs, for very particular effects we want, out of the fact that pancreatic enzymes are actually a cocktail of enzymes. There's a whole number of different ones, so we have a lot of key and block situations in a pancreatic enzyme. Conditions typically 30-35 degrees, 7 to 9, and running them for 45 minutes up to 5 hours maybe. In soaking, we also need enzymatic products these days. The technology has changed quite considerably over the last, say, 20 years. We need much quicker processing, we have much bigger vessels. So by having auxiliary in soaking that is based on enzymes, we can speed up the effect and do a catalytic reaction in all those effects that we want out of soaking. Soaking being possibly the most important process step in leather making. There we have basically the bacterial and fungal proteases because of the higher pH we require than in baiting, and we have of late the lipases. Why lipases became so interesting and so important in soaking is, let's take the particular product that we work with, the hide. Well, maybe 20 years ago we could do pre-fleshing, and for a number of reasons you don't find this a process step that we do any longer. It's too unsuccumable to take them out of the process to flesh. We have a lot of dirt stuck on the hair that will make it almost impossible to green flesh without making holes into the hide itself. So there's a lot of fat, and a lot more fat present today in a hide than there used to be even 10 years ago. We have trimmings, often the udder is left on a cowhide, which carries itself some maybe 3 kilograms of fat that we carry into the process of making leather, what used to be trimmed off. In older days, it was interesting to hear from Hugh Gilmore that there used to be a hide improvement society. Well, we certainly don't see much of this in today's age, not when you deal with particularly European hides that are full of dung, poorly flayed and badly trimmed, to the point of maybe even finding the entire head on the hide. Conditions in soaking typically in 9 to 10, so that's why we have usually not pancreatic enzymes in this process. And talking about a little bit of the lipase, now there's a concept that we've been following through to say, if there is so much more natural grease in the hide, mainly on the flesh side, why should we try to attempt emulsifying and degreasing the hide at that early stage? We will have so much fats being carried as emulsions into the effluent plant and excesses that are way out of proportion, that we found that a lipase product can do a very, very interesting job. Because it's a big molecule, it will not penetrate into the fatty layers in the cell-bound fat of the flesh side. It will only work on fat that is readily available in the grain, on the hair or on the wool. And it will, as a catalytic reaction, break down fats very quickly into fatty acids. In the presence of alkali, we produce then soaps. And these products are easily removed from the surface of the hide, which allows us to have better penetration of the follow-up alkali products that destroy the hair. There is the soaps that we form. I've spoken about this already. It's a self-supporting process because the enzyme is readily available throughout the entire process. As long as we provide alkali in the soaking process, we can produce the soaps from the fatty acids that have been split off from triglycerides. The lipase do tolerate high amounts of alkali. There is just a particular limitation to it. Having said what I said about the amount of fat in the flesh, if we have a situation of poorly preserved hides, we can find that fat cells break down during that process, and an excessive amount of fats being liberated into solution or into emulsion, that the lipase will actually struggle to deal with all this. Therefore, we actually strongly recommend that surfactants not being used in a kind of this kind of process, because they are the kind of materials that strip the fat out of the fat cells themselves. So by having a very clean surface on the grain, we allow liming chemicals to penetrate from the grain side faster. The natural protective layer that an animal has when it's out in the field has been destroyed by lipase. We therefore also get a much more uniform fat distribution, because the fat, cell-bound fat, the cell-bound fat is not being released. Therefore, we might even find improved fogging and waterproofing values. In liming and unhairing, we might want to also use the enzymes. It's all about the undesired materials we want to get rid of. And by using a catalytic reaction, we speed up that process as well. So from the old days of 48 hours process, from soaking and liming, to nearly a 24-hour process, we are forced to help the reaction along. Here the proteases need to be of very, very high alkali stability in the range of pH 12 to 13, of course. In summary, enzymes are extremely effective biocatalysts. They act at conditions close to physiological conditions, so it's important that you choose the right enzyme at the right stage in time of the process. They are environmental friendly. All of them at this stage in time are hydrolases. We want to destroy and remove all the undesired components in the hide. This is the reason why there are hydrolases that we use. They can be used in soaking, unhairing, baiting, and wet glue treatment. And important to say, any single component in the hide can only be removed once. So if you are using proteolytic enzymes in soaking and lining, you might find that in baiting there is very little left over. So you're just doing a cleaning process at this stage, whereas in the old days, you would have the entire process of breaking down the remaining unwanted proteins during baiting. So baiting has the process of baiting has shifted its responsibility somewhat to soaking and lining. As a postscriptum, some of it I've mentioned it already. There have been a drastic change in the industry over the past few decades. We have change in husbandry of animals. We have high preparation and trimmings that are today much to the detriment of our industry. We have preservation and conservation that have changed. We often work with green hides these days. We have waste issues, no green flesh in the best of times. The process size have increased, the time has decreased. We need to do energy saving with the help of catalysts, so we can save energy, we can reduce the amount of energy required to do the same kind of process. And we have pollution and undesirable chemicals that we can reduce thanks to the help of enzymes, or even eliminate with the help of enzymes. Therefore, it's important to have a good understanding of what enzymes do. It is foreseeable that biotechnology will allow us to even more engineer enzymes in the near future. Just in last month's issue of the National Geographic, they're talking about reviving extinct species. To do take a DNA from extinct species, revive them, maybe even implant an egg, a fertile egg into an elephant and produce a mammoth again. So what is possible, what they reckon is possible in the near future here, certainly applies to microbiology and biologic engineering to produce enzymes. There is a lot of interesting things coming up in the near future. Thank you very much.